Ready.
Action.
Hello, my dear students, and today, and I'm sorry I haven't gotten to this sooner, we've had lots of problems and other things come up. I want to finish the two labs that we're technically due Monday. We'll make them due this Friday. And I do want to tell you, I hope you're happy with your grades. You can check them in eSchool. Do not check your grades in Google Classroom because they're not weighted there. And y'all are lucky because if you didn't turn in a report, for the most part, I didn't put down zeros for everything. But from now on, you must do your work or you'll receive a zero. And you also need to start handing it in on time. I got a lot of work last week that had been due weeks ago. So if that's you, you need to keep up. I want to do these two labs. You know, I always take it late, but we have to start drawing the line. And I'm not always on time myself, so I know how that goes. But we've been studying the structure of the atom and the electronic structure of the atom, and we don't know how to look at and see how those subatomic particles, protons, neutrons, electrons, are truly arranged. All we can do is study their effects, and one of the effects is that when you heat up a substance, iron, an element, anything, it frequently glows. And what is happening? What's happening is you're adding energy to those electrons, elevating them to a higher orbital, and as they decay, they shed that excess energy as heat and light. And by decay, I mean go back to the ground state, to the original orbital they were in where they belong, because they don't belong in these higher energy orbitals. It's not energetically favorable for them to be there unless there's an input of energy. That energy does not have to be thermal energy. We're going to look at a couple of other ways of exciting electrons. One way is to pass an electric current through a substance. This is neon gas in this tube with a high energy current passed through it, and that excites the electrons. It's the same principle as in a fluorescent tube, except they subsequently fluoresce after they've been excited and given a chance to produce that light. But two things. That light, those electrons are in orbitals of a specific energy, and you excite them and they go up to a new orbital. And as we'll see, not today, but when we do an experiment with our spectrum tubes, the light they produce is very specific. Not a continuous spectrum like the white light from the sun or from this light that I have shining in my face right now, but of a very specific wavelength. And that tells me not only those electrons in specific orbits corresponding to specific energies, they are quantized. And by that, I mean they can only be in one orbit or the other. They walk up to the higher energy levels in steps, not a ramp. You can't go up halfway into a new energy level. You're either in this one or you're in that one. It's like walking up a ladder. You can't go up half a rung. There's nothing there. So I want to do a quick lab on chemiluminescence because there's some other ways to excite electrons and get them to produce light. One way is to use a chemical reaction to release energy that is subsequently absorbed by electrons in a molecule that excites them and allows them to move up and then decay or return to ground state with the emission of light of a specific wavelength. Now that happens in biological organisms as well. Certain diatoms, algae, certain animals, although it's frequently a symbiotic relationship as well. You've heard of the dangler fish, maybe in not Captain Nemo, but in Finding Nemo, or you've seen fireflies, okay? That is sometimes called bioluminescence, but it's just chemiluminescence in a living organism. using their metabolism and the chemical reactions that they carry out to produce light. That being said, we're going to look at chemiluminescence and glow sticks. So let's complete our laboratory instructions as outlined in the procedure here. We're going to take 3 commercially available chemical glow sticks, and we're going to investigate what affects them. So we're going to refer back to this when we start talking about chemical reactions, and also later when we start talking about rates of chemical reactions. I'm not going to put on my safety glasses because I'm wearing a face shield because of the COVID pandemic. Here I have 3 beakers of water, and I have 1 filled with ice, 1 standing at room temperature, and 1 I'm filling with boiling water from my tea kettle. So I use a tea kettle in the lab because it's quick and easy. I'm going to put on my glasses so that I can read the thermometer. I'm going to collect the temperature and record the temperature of all 3. This is a standard laboratory thermometer. We now tend to use ones filled with alcohol, colored with red food dye, and lots of people ask what this was. This is called a thermometer bumper. It just keeps it from rolling off. I noticed some of the students using it to remember setting it where the thermometer rose to, or the liquid inside the thermometer rose to record and remember it, but we'll remember our values. So if I put it into the ice water, if you remember, substances, most, water being an exception, tend to contract when chilled and expand when heated. And this is passing through a very thin capillary so that any changes are greatly magnified. Any chance we can focus in on this? So this particular thermometer has 2 different scales, but we want to use the Celsius scale. And it is at 2 degrees C because I started with cold water and ice straight from the freezer at -20. So this beaker is at 2 degrees. The room temperature beaker, we're at cool room temperature here in our classroom lab, is rising up to cool room temperature. I like the room a little cool, so the thermostat set down. It is going to 20 and a fraction, but just a fraction, not even 21. Yeah, almost 21. So we'll call this 21 degrees, cool room temperature, and the boiling water is going to send that liquid up high, up beyond it, all the way up here to 78 degrees. So we had 2, 21, and 78 degrees. And what I have here are some common, available at Walmart, common glow sticks. I'm going to release the 2 reagents, mix them together by breaking the thin glass membrane, separating them. It's hydrogen peroxide and some phthalate that then excites some specific dye that glows. But I'm going to break them and engage them. They're kind of bluish, purplish, bluish, this particular color. I'm going to mix them up the best that I can, and I'm going to set them in the different temperatures of water, and we're going to keep filming here, but I'm going to go turn out the lights so that our differences can be more dramatic. So This will only take 1 more minute, then we'll answer our questions.
Okay.
So here.
That's one.
So let me replace this one to the cold, ice cold beaker. I think you can already see what effect temperature has on the chemical reaction. The point here is, this is an example of chemiluminescence using a chemical reaction. The energy contained inside of chemical bonds as they're broken and reformed, but energy is released. That energy is used or captured and used to excite an electron to a higher orbital, and as it returns to its ground state, it emits heat and light. So I have some cool room temperature water, some ice cold water, and some hot water, and you can see clearly this hot water one is much brighter than all the rest, and the dimmest one by far is the one in the ice water. So let's go back, answer our questions, answer your lab report, answer some questions so I can get you a grade. We'll do demo and discussion in one quick move here. Hope that this light works, and I did not test to make sure that my board is working. But, so we had 3 temperatures. We had a beaker at 2 degrees. Okay. I will help you with the discussion of this demonstration in the next video. Goodbye now.